Good evening, everyone. I hope I'm audible. Okay. Okay, so let's start today's session. Start with question number one. Suppose E and F are two Banach spaces. E and F be Banach spaces. And F is a function from E to F, which is continuous. Continuous map. And also there exists a constant. Suppose we can find some constant C positive such that norm fx plus y minus fx minus fy, this is less than C for every xy in E. Now since fx and fy are in F, so this is norm of F. And this condition says that the function f is almost linear. Almost linear. This says that f is almost linear. Then show that the function gx, if I define a new function g using the above function f such that gx is equal to limit n tending to infinity f 2 to the power n x. Now here 2 to the power n is just a scalar. We are multiplying scalar with the vector x and then operating f over it upon 2 to the power n. And this is for every x in E. Firstly, we'll show that this function is well defined. That means this limit actually exists, is well defined. Then we will see that this function g is a bounded linear function. G is a continuous linear map satisfying the condition norm g minus f. This is strictly less than k for some constant k. And this k is some constant. And since f and g are two continuous functions, on f and g, this norm is the norm on the space of continuous functions. That is the sup norm. This is the sup. So yes, using we started with the function f, which is defined on a Banach space and mapped to a Banach space. We'll be using the properties of Banach spaces. We are given that this function f is a continuous map and it satisfies some almost linearity condition. Using that, we constructed a function g in such a way. Then we will see that this function g is actually well-defined continuous bounded linear map. And in fact, it is not much far away from f. So this says that the distance between f and g is less than some constant. So basically, G lies on some ball around F. Let's see how we can. Let's start with some X in E, be arbitrary. Firstly, we claim that this G is well defined. That means let's claim 1. The limit n tending to infinity f2 to the power n x on 2 to the power n x. This sequence is convergent. Let an is equal to f2 to the power n x upon 2 to the power n. Obviously, this is a sequence in f. We need to show that the sequence an is convergent in F. And in fact, since F is a Banach space, showing that it is Cauchy is enough. In fact, since F is a Banach space, it is enough to show that the sequence an is a Cauchy sequence. That is, norm an minus am goes to infinity as n and m goes to infinity. So now let m and n be two natural numbers without loss of generality. Let n be strictly less than m. Then we have norm am minus an. This can be written as less than equal to just adding, subtracting the in-between terms. Am minus 1, am minus 1 minus am minus 2, and so on up to an plus 1 minus a. Now, eventually, we need to see the norm of the difference between two consecutive terms. Let's mark this as equation 1 and look at the difference between consecutive terms. Now, an plus 1 minus an for any n m n, this is equal to f of 2 to the power n plus 1 x upon 2 to the power n plus 1 minus f of 2 to the power n x upon 2 to the power n. This is directly by the definition. And this 2 to the power n plus 1 can be written as 2 to the power n x plus 2 to the power n x. And taking LCM, 2 to the power n plus 1, so this will be minus 2 times f 2 to the power n x on 2 to the power n plus 1. Now this implies norm an plus 1 minus an. This is equal to norm f2 to the power nx, 2 to the power nx minus 2 times can be written as separately. So eventually we'll be using the condition given on the function f plus 1. Now we were given this almost linearity condition. If I mark this as star, taking x equal to 2 to the power n x and y also 2 to the power n x. So from here, we'll get this is less than equal to c upon 2 to the power n plus 1. Replacing x and y by 2 to the power n x in star. Now the c is constant and we know that 1 upon 2 to the power n plus 1, this goes to. So we'll see that later. So let's mark this as number 2 and using equation 2 in first. So this implies a n plus 1 minus a n. This is less than equal to c upon 2 to the power n plus 1. We have a n minus a n. This is less than equal to. So when we can see that 2, the power of 2 is same as the subscript of the big great next term. So yeah, that will give us from here c upon 2 to the power m plus c upon 2 to the power m minus 1 and so on up to c upon 2 to the power n plus 1. So this is equal to taking c common. So we can write this as summation k from n plus 1 to m 1 upon 2 to the power k. So we know that summation 1 upon 2 to the power k is a convergent series and the tail of a convergent series always converges to 0. So from there we can write that this is less than equal to, so strictly less than epsilon for all n greater than equal or not n we will have. So this is less than equal to c summation k from n plus 1 to infinity 1 upon 2 to the power k. And now this is a tail of a convergent series. So this can be written as less than epsilon for all n greater than equal to n naught. Since summation k from 1 to infinity such that the summation, then we can write this n plus 1 also 1 upon 2 to the power k. We want this to be less than epsilon by c for all n greater than equal to n naught. So this n naught comes from here. Yeah, and hence this implies norm am minus an is strictly less than epsilon for all. So we have whenever n is greater than n naught, and also we started with m greater than n. Yeah, and m is greater than n. So whenever m and n both are greater than equal to n. This implies the sequence an is Cauchy in F, and hence convergent. This implies gx is equal to limit n tending to infinity f2 to the power nx upon 2 to the power n is well defined. And since x, we started with some arbitrary x, so I can write this for every x in E. Hence the function g is well defined. Next, we need to see that this function g is in fact continuous linear function. The linearity, I hope you can try yourself. I'll give hint for that. Claim 2 will be g is linear. You can start with showing that gx plus y will be equal to gx plus gy, and then for scalar multiplication, you'll have to start with some alpha x, where alpha is 2 to the power n. Basically, you'll be using the almost linearity condition. Using this further, you can prove that gp by qx, this will be equal to p by q times gx. That means we can scalar multiply for every for scalars in rational. And since rationals are dense in R, and since q is dense in R, you can eventually prove that g alpha x is equal to alpha gx for every alpha in R. So basically, the field that we have taken on the Banach spaces is the real space of real numbers. Then next comes the continuity. We have G is continuous. Now, since F is continuous, this implies if we define a sequence of functions h and x to be f2 to the power n x upon 2 to the power n, then clearly Hn is continuous for every n in n. Which will imply that, so yeah, it will be continuous at 0 as well for any epsilon positive. There exists delta positive such that norm Hnx minus Hn at 0, this is strictly less than epsilon, whenever norm x minus 0, this is less than delta. So basically we'll show that this g is continuous at 0, and we know that if a linear function is continuous at 0, it is continuous everywhere. Yeah, and Hn at 0, we know that this is f at 0.2 to the power n. This implies h in x minus f0 upon 2 to the power n. And in fact, let it be, this is less than epsilon whenever mod x is less than delta. Now taking n tending to infinity, so since hn, take limit n tending to infinity, hn x is nothing but the definition of gx. So this will be gx minus g0 as an epsilon whenever norm x is less than delta. Now this gives us that function g is continuous at 0. And since g is linear, this implies g is continuous on E. Hence, g is a continuous linear function. Then we need to show that g lies in some how linearity of function guarantees that it is continuous. I think this was a result, some equivalent conditions for bounded linear functions. You must have done some characterizations. So we have that if a function f is linear, and then the following are equivalent conditions. Firstly, f is bounded linear function. Secondly, there exists some alpha positive such that norm fx, this is less than equal to alpha times norm x. Then we have f is continuous at 0. So yeah, this these conditions you have. These are called characterization of bounded linear functions. Okay. Next, we need to show that G lies in some neighborhood of F. So that will be our claim 4, norm G minus F, and this is the sup norm, is strictly less than K. Now for any X in E, what is this norm Fx plus H minus Fx?
Oh, ma'am, if f is linear, I think fx plus h minus fx becomes fx plus
FH.
fh minus fx, then fh.
Hmm.
So from there, linearity, I think continuity at continuity at zero implies
Yeah.
continuity.
Eventually, you get continuity on whole domain.
Okay.
Amount for any X in E, we have norm HNX minus FX. So you can see that this HNX was nothing but AN of our sequence if we fix this X. So I can write this as this is equal to AN minus A naught, where A naught is just Fx. So basically n equals to 0 in the definition of AN. So this can be written as less than equal to, as similarly as we had done earlier. So this will be less than equal to K from 0 to n minus 1, AK plus 1 minus A naught. Let me show you. the way we did for, yeah, from here, you can see that am minus an, this was less than equal to some constant summation k from n plus 1 to m, 1 upon 2 to the power k. So if I replace m by n and n by 0, this will be less than equal to summation k from 1 to n, 1 upon 2 to the power k. So yeah, that's what we are using here. So we should have k from, okay, so I can write it directly. This is less than equal to summation k from 1 to n c upon 2 to the power k. 2 to the power. Yeah. Okay. So as done earlier, and again taking n tending to infinity on both sides. So on left hand side, this is just gx minus fx. This will be less than equal to, and this is the infinite geometric progression. We know that when the radius is 2, this is c, 1 by 2 upon 1 minus 1 by 2. So this is just c. This implies norm gx minus fx is less than equal to c for every x in E, because the c is independent of x. Independent of x. So this implies the soup norm x in E, norm gx minus fx. Obviously, this is strictly less than c plus 1. I can take that to be k. This implies norm g minus f. This is strictly less than k. That's what we need to show. Okay. Next, we'll look at a problem of two problems related to the inverse function theorem. It means almost linear functions can be almost approximated by continuous function. F was almost linear and continuous. Then we can find a function g, which is which lies in a neighborhood of f, and obviously, yeah, that is continuous. Yeah, you can say that. But I don't know, approximated would be a good idea, because we can say that if this k was tending to 0, approximated means it's kind of equal, but we don't know whether this k is small enough. If we could make this k to be small enough, in that case maybe we can say that it is approximated by a continuous function. Hmm. So approximated we can't say, but yeah, we can say that such a function g lies in some neighborhood of f. Two. Suppose U is some subset of Rn and f is a function from U, subset of Rn to Rn, be a C1 smooth function. That means its derivative is also continuous. Be a C1 smooth map such that the derivative, we know that the derivative would eventually give us some matrix. The derivative map is invertible. That means the corresponding matrix is invertible at all points in U of U. Show that if V is a subset of U is open, that means if V is some open subset of U, V is open in Rn, it is a subset of U, then Fv is also open subset in subset of Rn. That means open set is mapped to open set. So for the case of continuous functions, we know that the pre-image of an open set is always open. But in this case, when our derivative map is invertible for all points, in this case, we can see that open sets are mapped to open sets. So for this, we'll be using the inverse function theorem. So let's just recall the inverse function theorem. So it is a very good and powerful tool in analysis. Function theorem. It says that suppose f is a function from, yeah, you can say that it becomes homeomorphism, because for homeomorphism we need our inverse to be continuous as well. In that case, yeah, yes. But I think local homeomorphism, because it need not be onto map. Something, I think it's called diffeomorphism. I'll see. So yeah, first start with inverse function theorem. Suppose f is a function from U to F. Suppose this is a subset of Rn and this is some Rm. Be a C1 map. And df at A, so it is a matrix, is invertible. Matrix and a linear transformation is invertible with Fa being matched to point B in F. Then we have the following. Firstly, this E is equal to F. Then we can find some open set. There exist open sets V and W in U and F respectively, such that A is an element in V and FV is mapped to W. That means this function F restricted to V from V to W. Now this is a bijection. Is bijective 1, 1 and on to. Further, if we define G to be the inverse of this F restricted to V, so obviously its domain will be W to V. Then this G is also a C1 mapping. G is also C1 with the derivative of G at any point Y. This is equal to derivative of f at gy, derivative of gy. Now gy is an element of v. F at gy is an element of w. So iska inverse for every y in w. Now for y in w, we have gy in v. Yeah, and f can be defined at gy. Iska inverse okay, so we'll see how we can use this inverse function theorem to prove the above result. So basically, all we need to show is that open set is mapped to open set. Solution. Now let's start with some v subset of u be an open set in Rn. Now since this F is a C1 mapping, we are given that F is C1 and DFA is invertible for all points of view. So by inverse function theorem, clearly this, yeah, we have from Rn to Rn. Then we need to show, we claim that this f of v is open in Rn. Now if I start with some point B belonging to fv, be arbitrary, we need to show that there exists an open ball around B which is contained completely in fv. So we need to show that there exists some R positive such that B belonging to BRB, this is contained in FV. So now since B, this is what we need to show. Since B, this is an element of FV, clearly we can find some A in V such that this B is equal to f of A. Now since dfx is invertible for every x in U, we get that dfa is also invertible. Since dfx is invertible, this is what we were already given, invertible for every x in U. Obviously, V subset of U. This implies dfa is invertible. And then by inverse function theorem, we'll be using the second point. By inverse function theorem, there exist open sets, a V closure. Sorry, not V closure, it's just V bar, or I should write V prime. V prime in U and W prime in F, such that this A is an element in V prime, which is a subset of V. So basically, we are taking V prime to be V intersection, the set that we get due to the second point of the inverse function theorem. So eventually, because we want everything to be subset of V, So I can write this as V1, where V1 is the set we will get due to point 2 of our just inverse function theorem. And since V and V1 both are open, we know that finite intersection of open sets is again open. We'll get V prime is open as well. And f V prime, this is equal to W prime. Now, since this B is equal to FA, A is an element in V prime, this belongs to F V prime. And F V prime, this is equal to W prime. This implies B belongs to W prime. Now, since W prime is open in F, since this W prime, this we got due to the inverse function theorem. W prime is open in F, we can find a ball. There exists R positive such that B is an element in BRB, which is contained in W prime. And this W prime, this is equal to FV prime. And this FV prime is a subset of FV. So if I let me mark these equations, this as, this one as 1, this one as 2. Yeah, we are getting this by second, and we got this by first, because V prime is a subset of V, FV prime will be a subset of FV. Therefore, B belongs to BRB is a subset of FV. Now, since B belonging to FV was arbitrary, therefore FV is open. Since B belonging to FV, that means for any arbitrary point in FV, we were able to find an open ball is arbitrary. This implies FV is open. And so that's what we needed to prove. I hope this is fine.
Ma'am, please give an overview again.
Okay. So mainly we are using the inverse function theorem to show that for any open set, if we start with some open set V, V in U, if this is open U, then f of V is open in the range set. So for that, we started with some arbitrary point in FV, and then we need to show that there exists an open ball, BRB, which is contained in FV. So that's what we prove in order to show that some set is open. So our aim was to show this. In order to show this, we use the inverse function theorem. So basically, we started with the fact that this B is in FV. FV means it is in range. That means there exists some A in V such that B is equal to FA. And now since F is invertible, the derivative of F at all points is invertible, we have DFA is invertible. So we can use the inverse function theorem. For inverse function theorem, we need two conditions. This F should be C1 mapping, that is already given, and DFA should be invertible. So now by the second point, we can find an open ball. Oh, sorry, open set. This second point says that for uh, since f of a was equal to b, we can find an open set V. So instead of V, I take that set to be V1. That means because V was already given. So we can find some set V1 such that A is in V1. This is open in the domain. That domain is our U. And then we have an open set W in, so there I took W prime in F, which is again open, such that A is in V1 and F of V1, this is equal to W. So instead of V1, then I took V prime to be V1 intersection V. That's because I wanted everything to be eventually so that this is a subset of V. Otherwise, it's same. Yeah. So from there, so yeah, we should write instead of W prime, then again, this should be taken as W1, and then we take W prime to be W1 intersection F of V.
W1 intersection F of
No, no, no,
B.
no. Because F of V, we don't know whether it is open, no?
Hmm. Um,
We
why we are
have
taking intersection?
so that I get this subset. I get this V prime to be subset of V, so that from here I get this ball is contained in F of V.
Oh, okay, okay.
And we can find some V prime. This it should be mapped up. Eventually, the idea is to use the second point only. So, because from second point we can see that open set V is mapped to open set W. That's what we are mainly using. And this V is an open set containing A. So eventually any ball around A is mapped to some ball around FA in W.
Okay, ma'am.
So that's what we need to use. I think I'll have to check this again. This point of intersection, this argument, I'll have to check again.
Here V1 is open in Rn, I think, no?
Yeah, Rn. Everything is in Rn.
So actually, B prime is open in U and U is subspace of Rn. So any open set
No,
in
no, it's not
subspace is in the
subspace.
form.
No, 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 it's not that open subspace kind definition. U is just a
Uh,
subset of Rn. So when we are
um,
saying that V is subset of U and it is open, that means V is open in Rn and it is a subset of U.
oh, okay.
No, no, what you said that if we consider U to be the subspace and we
Hmm.
say that V is open in U, that means V is equal to some
Some
A
open set
intersection U, where A is open in
Rn.
Rn. Yeah, with that, I think From there we'll get this condition, no? Something like
Yes,
this.
ma'am.
Okay, okay, okay. Yeah, yeah, you're right. Because it was nowhere written that U is subspace. So we should
Mm.
consider that subspace definition. So we should start
Mm.
with V is open in U. Okay. Yeah, with that we can do.
Yes.
Okay.
When we
Yeah.
are saying V is open in U, it
Hmm.
means U is subspace, I think. No? Then we can say the
Yeah, yeah.
existence of open set in a subset, I
And
think.
in that case, we get this intersection kind of thing.
Mm.
I'll do the proof again with this argument. Maybe we can do that. I'll let you know. Okay. Next question. Let M be the space of all n cross n square matrices. Script M be the space of all n cross n square matrices, and let f is a function from M to M defined as f of A is every matrix is mapped to its square. Show that for some open set V around identity matrix and identity matrix, we can find two different C1 smooth maps. G and H from the space M to M, and in fact from some W, where W is some subset of M, such that if B belongs to W, this is some subset of M, GB square is equal to HB square, and this is equal to B. Now, since we are getting the square of GB and HB to be same, so it might, you can think that they are something of the form negative of each other, because we know that only for we know that for x and minus x square, in both the cases the square is same. So anyways, the difference between both the functions would be just their sign. So again, we'll be using the inverse function theorem. Okay, let's start with looking at the derivative of this map
This
F.
is W or V?
W, any subset. Show that for some open set V around. Okay, this, no, this will be some other set W.
Oh.
That will come, this W will come eventually by this W. This W.
Oh.
Hmm. Okay, let's start with the derivative. Derivative, we'll see that its derivative is invertible or not. Then only we can apply the inverse function theorem. So firstly, let us find the derivative of f of small f at some in f. So we have f of a plus h minus f of a. This is nothing but a plus h square minus a square. We know that by algebra of matrix. This will be a square plus ah plus ha plus h square minus a square. This is x square plus ah plus ha. Now if I define, if we define dfa at any point b to be just ab plus ba, then we'll get f a plus h minus fa minus dfa at h upon norm h. This will be, so eventually everything will get cancelled out. Minus ah plus ha upon norm h. This is just, this will be less than equal to norm h square upon norm h, because we know that for operators norm ab, this is less than equal to norm a times norm b. So this is just norm h, which will obviously go to 0 as h goes to 0. So therefore, by the definition, this dfa is actually the derivative of the function f. And clearly you can see that this is a bounded linear map. Continuous, it is continuous linear map. You can check the linearity yourself. And this dfa at any point b, this norm is, this can be written as less than equal to norm AB plus norm BA by triangles inequality, and again by this condition this will be less than equal to 2 times norm A norm B. And this is happening for every B. This implies this DFA is continuous linear. So therefore this serves as our derivative. Therefore this map F is differentiable on M with DFA being a map from M to M such that DFA at any point B, this is nothing but AB plus BA. This is for every B in M, and this is happening for every A in A. M. Therefore, this F is differentiable everywhere. From here, we get that again it is differentiable at identity also. DFI, this is a map from M to M, and DFI at any point B, this is not just B plus B, so that will be 2B. So eventually this, the derivative of F is just, if we try to represent this derivative map by some matrix, so it will be eventually a diagonal matrix with diagonal entries 2. So this DFI If we write it in the matrix form, this will be 2, 2, 2 and 0 everywhere. So now since this is invertible, therefore dfi is invertible, and hence we can use the inverse function theorem. Does all these operators give similar interpretation when we consider the matrix as n square tuple? So are you asking about the derivative? All the operators give similar the derivative, when we are considering the matrices. For the case of matrices, you'll get a derivative in this form itself. So for matrices, it is comparatively easier to find the derivative. You don't need to find the Jacobian and all those things. In fact, this is also a good way to start if you want to find derivative of some function. Start with f of x plus h minus f of x. See that if somehow by manipulation we can get this limit to be 0. Here we were directly getting some continuous map, that's why it was easier.
Okay.
Yeah, now this f is differentiable at I identity and its derivative is invertible. Therefore, we can apply the inverse function theorem. This implies by, again, we'll be using the point 2, by inverse function theorem, there exist open sets V and W in M such that this identity belongs to V and FV is equal to W. So from here we get this W. So this gives us that F restricted to V, which is a map from V to W, is bijective, hence invertible, bijective. And if we define a function g to be equal to the inverse of this F restriction over V, which is a map from W to V, then we know that G is also C1 by point 2. Now for any for any B in W, now for any B in W, GB whole square, this is equal to, so GB is nothing but F inverse, F restricted to V inverse at any point B, the whole square. This is equal to A square, where A belonging to V is such that f of A is equal to B. That is, A square is equal to B. So this is A square, and we know that A square is equal to B. Therefore, we get GB square, this is equal to B. Now, if we take just negative of this function g, suppose I define some map phi. So this is our first map. Now, define phi from M to M, which maps A to minus A, and then compose it with G. Clearly, this phi is a C1 map. And if I take H, which is phi composed with G, is C1. Yes, yes, inverse function theorem is very powerful. It's used at a lot of places. This implies for any b in W, hb square, this is equal to pi gb square. And gb, we know that gb is a, this is equal to phi a square, where a belonging to v is such that a square is equal to b, and phi of a is nothing but minus a. This is, and again we know that a square and minus a square are same. So this is a square. This a square is equal to b. Therefore, hb square is equal to b. Hence, we got two distinct functions such that for any b in this W, gb square and hb square are equal to this function, this matrix B. Okay, this is fine. Let's move to next question where we'll be using Taylor's expansion. Now suppose f is some C2 smooth function. F is a function from U to Rn, be a C2 smooth map. And suppose x is the root of f, that means fx is equal to 0 for some x in U. Now assume that this dfx, derivative of f at this x, is invertible. And since we know that the set of all invertible matrices is open, so we can find a ball around this x such that every yeah, so let B be a ball around x such that this dfy is invertible for every y in B. Now using this B, let us define if a function n from B to Rn such that ny, this is equal to y minus dfy inverse, because dfy is invertible, times f. Then show that we can find R positive such that for each y in V with norm y minus x less than R, that means if suppose this is a ball B, this is a point X, then we can find a ball around X of radius R for any y belonging to this ball, the sequence the sequence y n y n n y and so on converges to x. So basically it is kind of some contraction mapping that eventually the sequence will lead us to the root, or if I take this n is something. Okay, we'll explain that. So eventually we are converging to some fixed point of this map n. Okay. So we have ny. This is equal to y minus dfy inverse fy. This is for every y in B. This implies nx, this is equal to x minus dfx inverse. We know that dfx is invertible, so this inverse is well defined, times fx. Now we were given that x is root of f, that means this fx is 0, so eventually this is equal to x. That means this x is a fixed point of n. This implies x is a fixed point of. So let me mark this as equation 1. Now let's differentiate this function n using the product and then the chain rule. Uh, uh, so I can write this n y. This is equal to, so I can replace this y by iy. So nothing, just the identity map minus d fy inverse f. This implies dny. This is, since the derivative of identity map is identity, so this is, then here we'll apply the product rule. So derivative of the first term, second term as it is, plus first term as it is, inverse, and derivative of second term. This is dfy inverse. So this is basically multiplying a matrix with its inverse. So eventually that will give us identity. So yeah, this and this will get cancelled out. This is just minus d dfy inverse fy. And since dfy inverse is again a matrix, so for matrix, this will eventually give you, yeah, instead this implies dnx, derivative of n at point x. This is just minus d dfy dfx inverse times fx. Now since fx is 0, this is 0. Therefore, dnx is equal to 0. Let's mark this as 2. Now by Taylor's expansion for C2 functions, we know that Taylor's theorem, this ny, this n x plus y minus x, this is equal to nx plus dnx at y minus x plus some terms, some remainder term. I'll write that as this big O norm x square. This means that that was some remainder term, that is this remainder term, its norm is less than equal to some constant times norm y minus x square. So basically this big O, we can write this big O represents something that is less than equal to this. Now I'll explain you. So if f and g are such that fx is less than equal to some constant times gx, then we say that fx is equal to big O gx. So this fx can be yeah, that's what I'm explaining. So this big O basically it tells you that the growth of the function f is lesser than gx. So basically, if gx is going to 0, so instead, yeah, some positive functions uh, such that its modulus is less than c times gx. So this tells us that whenever the bigger term, the term inside big O, whenever this goes to 0, the term that is replaced by this also goes to 0. So that means here we had some remainder term whose growth is lesser than this norm y minus x square. Okay, did you get this big O idea? Why we are using, how this big O term came into consideration? We'll see how this will be helpful for us. Okay. So from here, now since dnx is 0, this gives us ny and nx is equal to x minus x. This is equal to big O norm y minus x square. Now this means that norm of ny minus x, this is less than equal to.
Ma'am, what is fx here with respect to big O?
So this is
Gx
just
is norm
definition.
y minus x square.
I'll tell. Here, that fx is the remainder term of the
Oh,
Taylor's theorem. Okay, let me bring that again. So here this f here, it is the remainder term. Basically, that remainder term will have some terms of the form u minus x square, then you'll have u minus x cube and so on. So whenever this is small, so u minus x square will be the largest. We know that when the number is near to 0, the lesser power is the bigger one. So basically, we are taking this y tending to 0, that will give us norm y minus x, as y tends to 0, sorry, y tends to x. That means when y is closer to x, we have y minus x. This is tending to 0. That means y minus x is some term that is very close to 0. That means clearly it is lesser than 1. So that will give us that y minus x to the power n. So remainder term has some this kind of term, no? This will be lesser than equal to
yes.
norm y minus x square for every n greater than equal to 2, because this term is small. So eventually,
Oh,
our remainder term will have some y minus x square, then some larger power, which can be made lesser than equal to some constant times y minus x. This constant will obviously depend on the function n. So I'm replacing all those terms by big O y minus x square.
okay,
So
ma'am.
now, uh, so now this implies that this is less than equal to some constant times norm y minus x square. Now this will help us to prove the convergence of the sequence. Let me mark this as point 2. Now let's define the sequence. Let y naught be equal to y. This y is something close to x. We'll see that how close this y we need. This implies we are constructing the sequence. Y1 is n y naught, y2 is n y1, and so on. Yk is n yk minus 1. And we want to show that this yk sequence converges to x. Now, norm yk minus x, this is equal to norm nyk minus 1 minus x. Now, this is less than equal to c times norm yk minus 1 minus x by above equation 2. Square, we'll have square also. Now, this is equal to nyk minus 2 minus x square by definition. And again by equation 2, this is less than equal to c. So yeah, we'll have again, this time we'll have c square and yk minus 2 minus x to the power 4, because we are taking square on the left hand side of the second equation. Okay, this is again by equation 2. Yeah, so we can write this to be c to the power 3. 3 can be written as 4 minus 1 norm by k minus 2 minus x to the power 4. You'll see why I took it this way. Now again, this will be equal to e to the power 4 minus 1. Yk minus 2 is nyk minus 3 minus x to the power 4. Then by equation 2, this will be less than equal to c to the power 4 minus 1 as it is. Then we have c to the power 4. And this will be yk minus 3 minus x to the power 8. Yeah, square to the power 4. So from here, I'll get c to the power 8 minus 1 yk minus 3 minus x to the power 8. And so on. You can see that this will be less than equal to c to the power some 2 to the power, because everywhere we had 4, 8, and next step we'll get 16. So some 2 to the power minus 1 and y. So here you can see that whenever we have we had k minus 3, we had 2 to the power 3. When we had k minus 2, we had the power of c was 2 to the power 2 minus 1. So if I want here to be y naught, so that would be yk minus k. In that case, I should get c to the power 2 to the power k minus 1 minus x. This to the power again 2 to the power k. This 8 and 8 is same, 4 and 4 are same. So this is equal to c to the power 2 to the power k minus 1 y naught minus x to the power 2 to the power k. Okay. So now if I take, yeah, this y naught was nothing but just y. This is equal to c to the power 2 to the power k minus 1 norm y minus x to the power 2 to the power k. Now if I take this norm y minus x to be strictly less than r, in that case we'll get norm y minus x to the power 2 to the power k strictly less than r to the power 2 to the power k. Should be something minus 1. From here, we'll get from yk minus x. This is less than equal to c to the power 2 to the power k on c, because we have minus 1 also. Now this we want it to converge to 0, so that we want this to go to 0 as k tends to infinity, so that the sequence yk converges to 0. Now if I take this r such that r times c is strictly less than 1, in that case we'll get this convergence.
yk tends to x or 0?
Yk tends to x.
Oh,
Now if we take r small enough so that this rc is strictly less than 1, then we know that obviously rc to the power 2 to the power k, this will go to 0. And that will imply that yk minus x norm, this is going to 0 as k tends to infinity. So this implies yk converges to x, provided for norm y minus x less than r, where r is such that rc is strictly less than 1. The c is coming due to the Taylor's theorem. Eventually it is depending on the function n. Hope this is fine. Okay. Let's move to next question then. Something related to Taylor's theorem. So let T be a polynomial from Rn to R of degree k. Now fix some A in Rn, then show that firstly this Px is equal to tkp0x, where tkp0x is the Taylor polynomial. So yeah, we call it Taylor polynomial of degree less than equal to k. Yes, we have pt f a x. This is by definition summation mod alpha less than equal to d 1 upon alpha factorial del alpha f at a times x minus a to the power alpha, where this alpha is multi-index. That means alpha is some tuple f1, alpha 1, alpha 2 up to alpha n, where these alpha i's are natural numbers, and this mod alpha means alpha 1 plus alpha 2 to alpha n. Alpha factorial means alpha 1 factorial, alpha 2 factorial, alpha n factorial. Then x minus a to the power alpha means, now since x is in Rn, x minus a is again in Rn, so it is again an n tuple. So this means that we are just taking alpha 1 power of x1 minus a1, then we take alpha 2 power of x2 minus a2, and so on up to xn minus an alpha n, and this del alpha f at a, this is the partial derivative of f mod alpha times, so with respect to first variable alpha 1 times, with respect to second variable alpha 2 times, with respect to nth variable alpha n times. Okay, then second part, it says obtain an expression for px in terms of dkpax. Then third part says that if q is some other polynomial, r into r is another polynomial of degree less than equal to k, such that limit h tending to 0 ph minus qh upon norm h to the power k is equal to 0, then this p is equal to q.
Ma'am,
Hmm?
how
Yes.
can we see this? How to see this Taylor polynomial of higher dimension to Taylor polynomial of one variable? Can we relate to
This
understand
Taylor
this?
polynomial. Yeah, yeah,
Yes, ma'am.
I'll start with first part for n equals to 1. We'll do this for n equals to 1 and n equals to 2. Then further you can try yourself.
The definition of Taylor polynomial of higher degree. How can you
This
view?
definition, huh?
Yes, ma'am.
Yeah,
How to
yeah.
view it
I'll
in one
explain.
variable case?
Yeah, I'll start with one variable and then for two variable also. Solution. So firstly, let us start with n equals to 1. So in this case, our px is a polynomial of degree k. So it can be written as a naught plus a1x and so on up to ak x to the power k. So in for case n equals to 1, instead of partial derivatives, we will have direct derivatives, because yeah, there are no partial derivatives for one dimension. Now from here, we know that this p at 0, this is a naught. P dash at 0 will give us a1. P double dash at 0 will give us 2 times a2. P triple dash at 0 will give us 6a3. So basically that is 3 factorial times a3, and so on. The kth derivative at 0, this will give us k factorial times ak. So from here, we can write this px is equal to, so I can replace a naught by p0, then a1 by p dash 0 times x, then a2, this is 1 by 2 times p double dash at 0. So this is 1 by 2 times p double dash 0, x square, and so on up to this is 1 by k factorial p, kth derivative of p at 0, x to the power k. So this is equal to summation alpha from 0 to k, 1 upon alpha factorial, alphath derivative of p at 0 times x to the power alpha. So this is the one-dimensional version of the Taylor's polynomial. I hope this is clear, this one-dimensional version.
Yes, ma'am.
Hmm. So this can be written as tk p0x. Therefore, this px is equal to tk p0x. So yeah, let's do something for n equals to 2 also. Let's take n equal to 2. So now we have two independent variables. So if I start with, suppose k equals to 0. K equals to 0 means the polynomial is just a constant polynomial. K is equal to 0, and that means the degree is 0. That means the polynomial p x is just a constant, which can be written as p0. So yeah, this is just summation mod alpha less than equal to 0. This is nothing to do. 0 to the power alpha, which is p0 p0x. Then for k equals to 1, we are px. This is something of the form a naught. Instead, I should write c naught. C naught plus a1x plus b1y or x1, x2. Right? x1, x2. Now again, this p0 is equal to c naught. Del p by del x1 at 0, this is a1. Del p by del x2 at 0, this is equal to b1. So I can write up polynomial px. This is equal to p0 plus del p by del x1 0, x1 plus del p by del x2 at 0, x2. So I can write this as the 0th derivative of p at 0 plus, so taking alpha, the multi-index alpha to be 1 comma 0. So this is del 1 0 p at 0 times x to the power 1 comma 0 plus del 0 comma 1 p 0 x to the power 0 comma 1. So this is equal to summation mod alpha less than equal to 1 upon alpha factorial del alpha p0 x to the power alpha. Yeah, because this mod alpha equal to 1 can be made only for the case alpha equals to 0 comma 1 and 1 comma 0.
Ma'am, what k represents here?
K represents the degree of the polynomial,
Oh,
highest power. This can be written as P1 P0x. Yeah, similarly, you can look for higher dimension and higher degree. Similarly, yeah, for higher dimension and higher degree. Hmm. Second part, we need to find the expression in terms of tkp ax. So instead of 0, so instead of x to the power alpha, we need something of the form x minus a to the power alpha. Find expression for p in terms of pk pax. So now since px is a polynomial of degree k, it is an element of the vector space of all polynomials of degree k. Let V be the space of polynomials of degree at most k. We know that this V is a vector space and P is element of this P, Px. Also, we know that the set x minus a to the power alpha, where alpha is the multi-index with mod alpha less than equal to k. This set S, or I'll write it as beta. The set beta is forms a basis for V, forms a basis for V. This implies we can write this B Px to be summation mod alpha less than equal to k, some d alpha times x minus a to the power alpha. Just the linear combination of vectors in the basis. Now, differentiating both the sides with respect to each of these alphas, will get d alpha, or I'll write del alpha px. This is summation mod alpha less than equal to k. So yeah, eventually at point A, you'll get this to be equal to d alpha times alpha factorial. Yeah, because we are differentiating alpha times. You can see this start with dimension 1, 2, and then look forward. Eventually, you'll get something of this form, and this will give us that is these coefficients d alpha are nothing but del alpha pa upon alpha factorial. That is px. This is equal to sum. This is for every mod alpha less than equal to k. Mod alpha less than equal to k upon alpha factorial del alpha pa x minus a to the power f. So this was tk p a x. So yes, we can write this in form of some general point a as well. Next, we will show that which part you want me to repeat?
Ma'am, second part.
Uh, so basically, all we had done is start earlier. We know that for if we took the basis, so if we look for one variable, suppose we have polynomials in one variable, we know that in that case 1x x square x to the power n, this forms a basis of the vector space V of all containing polynomials of degree up to k. Similarly, we know that 1 x minus a, so I'll write this a, x minus a square, and so on up to x minus a to the power k. This will also form a basis for V. So that's the main thing that we are doing from first part to second part. In first part, we wrote our function p in some linear combination of x to the power alpha, the form of linear combination of x to the power alpha. In second part, we are writing it in as some linear combination of x minus a to the power alpha. In that case, just the coefficient will change. Here the coefficient was p0, del alpha p0 upon alpha factorial. In this case, we'll get del alpha pa upon alpha factorial. So yeah, we start with this linear combination, and then you can
And
try
this
this. Yeah,
and this A is a vector in Rn or
Rn, Rn. Uh, our domain was Rn, no? Yeah. So x minus a is well defined.
yes. Okay.
Okay. Next, we will show that if q is some other polynomial with degree less than equal to k satisfying this condition, then this q should be actually equal to p. So for this, we'll use the Taylor's theorem without remainder. So let's recall that. Let's recall. Taylor's theorem without remainder. Let f be a function from u to r, which is ck smooth. Then, firstly, the Taylor's polynomial tkfax approximates f up to order k. That means limit h tending to 0, f of a plus h minus tk fah upon norm h to the power k, this goes to 0. That means tk is somewhere going near to fa plus h, fa, because h is tending to 0. Secondly, if qx is some other polynomial, if qx is another polynomial such that this limit h tending to 0, fa plus h minus qx upon norm h to the power k, this is 0, then this q is actually equal to tk. That means this tk is unique. That's the idea we'll be using here. Now let us define. Let's see the problem again. We are given some q that satisfies, let's suppose this is star, that satisfies the equation star. Now define a new function Rx to be px minus qx. We'll show that this r is nothing but 0. So we are already given that. We are given that limit h tending to 0 r h upon norm h to the power k, this is equal to 0. Now since p and q are polynomials, hence r is again a polynomial of degree k, or we can say at most k, because q has degree at most k. Since p and q are polynomial of degree at most k, this implies r is also a polynomial of degree less than equal to k. Then again, as done in first part, I can write this r h to be equal to summation mod alpha less than equal to k 1 upon alpha factorial del alpha r at 0 h to the power f, which is basically tk r 0 h. Now since limit h tending to 0 r h by h, this is 0. I can write it as limit h tending to 0 r h minus 0 by now h to the power k. So this implies this as, so we'll use this condition. Yeah, taking a equals to 0 in part 2 of the above theorem. So I'll this is the theorem, Taylor's theorem. Taylor's theorem without remainder. So taking a equals to 0 in the above theorem, by first we know that if this q is 0 here, satisfying such condition, then q is equal to tk. So from here 0 is equal to tk, r, this is tk f a h, sorry, q x, this is equal to x. So from here this will be r a 0, and we know that tk r 0 x, this is equal to rx. So I should have marked this as 1, this as 2. This comes from this. Therefore, Rx is equal to 0, that is P is equal to Q. That's what we wanted to prove. So eventually, a polynomial itself is the approximated polynomial for that function. So is it fine? So I guess this is it. Okay, we'll meet next Sunday and continue with this. Okay, then.